So let's go ahead and finish Module 2 by looking at Part 2 of the physical connections that we use to create all these magnificent networks and the internet. So we're working on the coolest part, which is definitely fiber optic cabling. So let's look at fiber optic cabling and sort of compare it with our traditional Ethernet. So first of all, Ethernet is definitely susceptible to electromagnetic interference and radio frequency interference. And in the case of fiber optic cabling, because it's not transmitting with those, we don't get that interference. So that's one thing that makes it great. Of course, the difficulty is its cost. So pros, it's immune to EMI and RFI like we talked about. Definitely longer distances. So Ethernet, 100 meters. Here, 40 kilometers or about 25 miles in a single hop. Give you an idea there of what fiber optic cabling traditionally looks like. Of course, we've reduced the expense by taking that glass cladding and, making it plastic. Also easier to handle that way. Cons, it is difficult to install, more expensive than twisted pair. For now it is. Troubleshooting equipment is expensive and definitely more difficult to troubleshoot. So if you've ever thought about it, we have to polish those ends just right so that light can transfer through the cable correctly. So a couple different types, single mode and multi-mode. Multi-mode fiber optic cable that uses light to communicate with the signal. It's dispersed in numerous paths. So you can see multi-mode in the graphic below and single mode above. So, of course, with single mode, the throughput's going to be faster. With multi-mode, the throughput would be less, but, can carry more signals. So, advantages, disadvantages on both. So, provides, high bandwidth and high speeds over medium distances, up to about 3,000 feet. So, for multi-mode. So, single mode, very high speed because if you think about it, we're transferring. So there's a nice graphic sort of comparing, both can be glass fiber, plastic, simplex, duplex, standard connections on both, but multi-mode, lower bandwidth, higher attenuation, of course, because we're sending multiple signals. Single mode, high bandwidth, low attenuation. So it just depends on what we need. So, and depends on how far we're needing to travel. So lasers, primary light sources, spans very long distances because it can transmit data 50 times farther than multi-mode fiber. So that's that 40 meters. So a couple connectors to look at. Here's a nice graphic of the standard 4 connectors for fiber optic. So here we have the SC connector. Go ahead and pause the video if you'd like to look at these closer. The straight tip connector. The small form factor connector, and then the local connector. So, used for fast storage area networks, gigabit Ethernet. So, this is the connector that we use for storage area networks standardly. So, installing, many components involved in wiring computer network, cables, of course, connectors, cross connects, patch panels, jacks, devices, connectors go into, etc. So, cross connect is a location within a cabling system where all wires come together, typically into, patch panels, patch cables. So what we have is we have the wiring in the building, okay, which is on one side of the patch panel. And then we go ahead and wire those into, say, our switches, or other devices. So we use a patch cable. Now, one of the secrets or things that I like, when you get a bunch of these patch cables together and they're all blue, it can be very difficult to decipher what's what. In a lot of the networks I've set up, especially large networks, what I tend to use is use different color patch cables depending on what I'm patching. So if I'm patching a desktop, it might be blue because that's the most inexpensive cabling there is. Printers might be yellow, access points might be red, et cetera, and so on, just so it's easier for me to look at that patch panel and find what I may be looking for. So, here's a great example of, the back of a patch panel. So this is all the wiring coming from the building, all those patches into offices, into conference rooms, etc. So a couple things, back in the day, the idea of older sort of punch downs where we actually would use the old phone blocks to punch down cabling. Now pretty much patch panels like this, are used. There actually is a newer style patch panel where these are actually snapped in. So more like a patch panel in a wall. It just makes it easier. These can be really cumbersome to wire. So the new style allows you to wire it away and then just snap it into place within the patch panel. So here's an example of that 66 block. It's unsuited for network connections, faster than 10 megabits. This is what we used to use. This is what we used for phones. So we would wire one side in to the building and the other side into the extension. So considered legacy for sure. Let me go back here. And 25 pair capacity. So MDF or IDF, a main distribution frame. So here's a great example. This is all the wiring coming into a building. Typically when we see this, it tends to be phone, old phone. Now patch panels are voice over IP and can be our data network as well. So intermediate distribution frame, located in an equipment room or telecommunications room. So again, a lot of times what we'll do is we'll have a main that goes up to IDFs at say each floor level in a building, and the main would be what comes in from the street into the main, and then we go the main to the intermediate to the different floors in a building, and then from there we can wire out to the different offices and locations within that floor. So there's a great example. Standard 110, so one side has RJ11 jacks for phone connectors or RJ45 jacks for network connectors, and the other side. So similar, as you can tell, to a modern patch panel. So the demarc or demarcation point is the last point of responsibility of the service provider. So this might be an example that Ben Broadband says, okay, look, where the wiring comes into your house, boom, that's where we're responsible for. Of course, Ben Broadband extends that because they'll bring it into the house to make sure it works. But in a lot of cases, especially in wiring big buildings, Ben Broadband's going to bring theirs to the building, and then you're responsible for certifying that it works within the building in a lot of cases. So especially with phone companies. So Smart Jack, also called a network interface device, owned by the public switch telephone network. Special network interface often used between the service provider's network and an internal network. So again, in large instances, we would find one of those. So what can go wrong? Well, first of all, thinking back to lecture 1, copper cables placed too close to magnetic source. Attenuation, running them too long outside of a spec. As we put the RJ45 connector, we don't make a good connection on cable 4. So, the biggest thing is make sure you're testing your cables, certifying that the cables are good, and that you're handling all the cables well, putting them in places that they're not going to be moved around. Probably one of the greatest examples is, if we wire something in and we use a patch cable that's really long and we just allow it to hang, first of all, it looks terrible. But second of all, that the actual weight of the cable might actually affect eventually how it's, plugged into the connector. So, good idea to shorten those, make them as long as they need to be. Run them in cable organizers so that the weight of the cable doesn't affect the connection. And that's something that, you can plug it in today and it works just fine. And a year from now, just that weight has been pulling on that cable. So something to keep in mind. Always when we're wiring, label every single wire, label every single patch panel. It is such a challenge to find, hey, there's a punch down and it's in this office and it's not labeled, and now I somehow have to take a toner, plug a toner in there, go back and find it in a patch panel that has 600 connections. So if we label everything when we set it up, we're going to be a lot better off. So then, in terminating, again, test, make sure things are terminated correctly, make good connections. I've seen a lot of connections where there is Ethernet cable. I'll see if I can find one. Hold on. All right, so I've added an example right there. Poor termination. In this case, here's an RJ45. First of all, it's not going to plug in well if we leave a wire hanging out the front. And here's one of my biggest pet peeves, and that is this little lock lever right here is actually designed to lock around, the protective coating, the outside layer of the wires. So what we need to do is actually bring this up and cut our wires to where they're equal here, and this is inside the RJ45 connection. So I've seen these where people will just connect these so poorly, that there's a couple inches here. And then, of course, the problem is, those wires are exposed. They're much easier to damage. So just something to sort of keep in mind, quality. So let's briefly move on to wireless. We're going to talk more about wireless later in the course. But, 802.11 is the standard IEEE. We started with A, really didn't grab hold. It wasn't until 802.11b that we really grabbed hold, and that's where wireless sort of took off, I should say. Since then, we've seen the Rev G, N, and AC all become standard. So 802.11 is the most prominent standard for wireless LANs. It addresses distance, speed, latency, frequency, number of channels, bonding channels, and MIMO. So 802.11a, theoretical. I love how they sell wireless now, because if you notice on the outside of the boxes, they're showing the theoretical maximum throughput, not the realistic throughput, not what you should expect to get. So, briefly, here's A. Go ahead and pause the video if you want to look at A. I'm going to jump to B, though. This is where, my first experience with wireless was, and having an 802.11b wireless router in my home. So theoretical throughput was 11 megabits per second. Realistically, we'd be looking at about 2.5. So, maximum indoor range, 150 feet, 45 meters, outdoor, etc. Again, this indoor range depends on what construction materials are used. So if we're in a steel building, where the signal is going to bounce off versus go through, that range is going to be much shorter. So go ahead and pause this. I'll go through these pretty quickly. Pause them to get more detail. There's G, so again, 54 megabits, 22. Basically half was the realistic throughput. So, the idea of, full duplex throughput. So sending and receiving signals 22 meg. So fully backward compatible. Most of the wireless access points that we're seeing, the wireless routers, will support the current IEEE standard and then the backwards, so that our old devices will connect as well. So 802.11n, that's probably what most of you have. So, again, 300 to 600 megabits per second. Theoretical, realistically, 100. So there's still the fact that if you have 802.11n, depending on where your router is, how many devices are connected, theoretically the idea is we're supposed to be able to connect 244 devices. But if each one's taking up part of that throughput, they're not going to work well. And of course, these standard home devices aren't designed for 50 nodes to be connecting to it wirelessly. So, make sure you're getting the device that you want. In my house, I've got 2 kids. They've got laptops. They've got iPhones. They've got iPads from school. We've got our, Blu-ray DVR, all of my computers trying to connect wirelessly. And it's certainly a load on a standard home wireless router. So, I definitely had to upgrade the router to get better throughput. So anyway, just something to consider. Uses channel bonding where two or more adjacent channels are linked together so that we can, increase that throughput. So, and then of course AC, as you know, is the current standard. So as we tie it all together, it's important to know, what types of media connect with what types of specific devices. Do we need a straight through cable, a crossover cable, rollover, whatever? Connecting the wrong type of media to a device, it's not going to work, of course. So let me give you the secret of this whole thing. In becoming IT professionals, here's the biggest thing I've seen in hiring a bunch of folks right out of school. The very first thing you want to troubleshoot is it plugged in? So a lot of people jump right to the logical side of things, start pinging around, etc., when literally what happened is overnight someone came in, they vacuumed, and that Cat5 cable got disconnected from the network interface card on a desktop. It's pretty simple. Make sure it's plugged in. Make sure the network interface card lights are working. And then also on the other end, sometimes, we'll come in on the weekends, we'll be working on patch panels, we'll unplug something that's in our way and forget to plug it back in. So, first of all, make sure that you're documenting what you're unplugging, that things get plugged back in, and of course, just check if it's plugged in. So if the power's not working on a computer, sometimes the easiest way is to simply plug it back in. So keep that in mind as you troubleshoot. So here's a little summary page that I landed on. Here's the second summary page. Pause if you want to get it. That's it for Module 2. You guys have a great day.